this episode, we're going to treat cloud capabilities the way a good security engineer treats any powerful tool, as something that can make you faster and more effective, but only if you understand where the new risks live. Cloud platforms give you incredible building blocks: centralized identity, automated deployment pipelines, container platforms, serverless functions, and richly exposed application programming interface, API, ecosystems, but those same building blocks can amplify mistakes. A small misconfiguration can be replicated across environments in minutes, and a weak permission can become the master key to dozens of services. The challenge for beginners is not memorizing vendor features. It is learning to see the security patterns that repeat across cloud services and to place controls where they actually matter. Cloud Access Security Broker, CASB, tools, secure CI/CD practices, container security, serverless security, and API security are all part of that pattern language. When you connect these topics, you start to see cloud security as an architectural discipline rather than a collection of separate checklists. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A good starting point is to recognize that cloud capabilities shift control from physical network boundaries to identity, policy, and automation. In traditional environments, a lot of security thinking centered on where the network perimeter was and what could cross it. In cloud environments, resources can be public by default if you misconfigure them, and access decisions are frequently made through identity and policy rather than through network location. That means the primary question becomes who can do what to which resource under which conditions, and whether those decisions are consistently enforced. It also means that automation becomes a major risk amplifier, because automated systems can create, change, and destroy infrastructure and code rapidly. Beginners sometimes assume automation is inherently safer because it reduces human error, but automation can also scale human error if the template or pipeline is wrong. Secure cloud implementation, therefore, begins with policy clarity, identity discipline, and strong logging, so you can see changes and verify that controls are actually working. Once you see the cloud as a policy-driven system, the tools we discuss make more sense as enforcement mechanisms at specific points. Cloud Access Security Broker, CASB, is best understood as a visibility and control layer that helps an organization govern how cloud services are used, especially when many different cloud applications are involved. A CASB can help you discover which cloud services are being used, enforce policies like blocking risky sharing behaviors, and provide monitoring and reporting across multiple platforms. Beginners often hear CASB and think it is a firewall for the cloud, but that is not the right mental model. A CASB is more like a policy bridge that helps you apply consistent rules to cloud usage that might otherwise be fragmented across different service interfaces. It can also help with data loss prevention, DLP, in cloud services by identifying sensitive content and applying controls that prevent it from being shared or exported in risky ways. The reason this matters is that cloud adoption often outpaces governance, and teams may start using services in ways that bypass traditional controls. A CASB helps close that governance gap by providing centralized oversight and enforcement, especially for data movement and access patterns. A CASB is most useful when it is connected to identity and classification, because policies become sharper when the system can distinguish between different users, devices, and data sensitivity levels. For example, a policy might allow external sharing of low-sensitivity documents, but block external sharing of highly sensitive data, or it might allow access to certain cloud apps only from managed devices. Beginners sometimes assume policies must be universal, but a policy that adapts to context is usually more secure and more usable, because it applies strong restrictions where they matter and keeps normal work flowing where risk is lower. A CASB can also provide important audit trails, showing who accessed what and how data was shared, which supports investigations and compliance needs. However, a key misconception is that a CASB replaces good configuration of each cloud service, when in reality it complements it. If the underlying service permissions are overly broad or misconfigured, you still have risk. The architectural mindset is that a CASB adds a cross-service control plane, but it must sit on top of disciplined identity and access management to be truly effective. Continuous integration and continuous delivery, CI/CD, is a cloud-era capability that turns code changes into running systems quickly, and it is one of the most important security focus areas because the pipeline is the factory that produces your software. When the pipeline is secure, it can deliver updates safely and quickly, including security fixes, which improves resilience. When the pipeline is weak, an attacker can tamper with builds, insert malicious code, or steal credentials that grant broad access to cloud environments. Beginners sometimes think the pipeline is just a developer tool, but in security terms it is a privileged system that can deploy infrastructure, update production services, and access secrets. That means the pipeline must be protected with strong access controls, separation of duties, and careful secret handling. It also means changes to the pipeline should be treated as high-risk changes that require review and auditing. A secure CI/CD design reduces the chance that a compromised developer account becomes a compromised production environment, because it constrains what accounts and pipelines can do, and it ensures that actions are traceable. Secure CI/CD also involves the idea of trustworthy artifacts, meaning you can prove that what you deploy is what you intended to build from the source you intended to use. That requires controlling dependency sources, verifying build outputs, and keeping a clear chain of custody from code to deployment. Beginners might think of this as overkill, but it directly addresses supply chain risk because many attacks target the build process for maximum impact. A secure pipeline also uses staged environments and progressive rollout so that changes are tested and monitored before they affect everyone. That is not just an operations preference. It is a security defense because attackers and bugs both cause harm when untested changes reach production quickly. Retesting is also part of the pipeline story because security fixes and security controls must be verified after changes, not assumed. In cloud environments, where infrastructure is defined and deployed programmatically, pipeline security also includes controlling who can modify infrastructure definitions. If an attacker can change an infrastructure template, they can create public exposure or grant themselves access, and the pipeline will faithfully deploy the attacker's changes unless controls prevent it. The lesson is that pipeline security is environment security because the pipeline is the mechanism that shapes the environment continuously. Containers are another cloud capability that changes how applications are packaged and deployed, and they bring both strong benefits and distinct risks. A container bundles an application and its dependencies into a consistent unit that can run in many environments, which improves portability and operational consistency. The security challenge is that containers can also bundle vulnerabilities, misconfigurations, and unnecessary components, and those issues can then be replicated widely. Beginners sometimes assume containers are inherently isolated like virtual machines, but containers share the underlying host resources in ways that require careful configuration and hardening. Container security begins with building minimal images, because smaller images have fewer components that can contain vulnerabilities and fewer tools that attackers can use if they gain access. It also includes vulnerability management for images, because vulnerabilities and dependencies are a common attack path. However, container security is not only about the image. It is also about how containers are run, what permissions they have, and what network access they are given. A container that runs with excessive privileges or broad network reach becomes a potential launchpad for lateral movement, which undermines the benefit of containerization. Runtime controls are critical for containers because deployment is not the end of the security story. Containers can be attacked while running, and if you cannot observe and constrain their behavior, you may miscompromise. That means enforcing least privilege in container permissions, restricting access to host resources, controlling how secrets are provided, and monitoring for suspicious activity. Beginners sometimes think secrets are safe if they are simply stored somewhere in the cloud, but secrets can leak if injected into containers insecurely or logged accidentally by applications. Network segmentation also matters, because containers often communicate with many services, and if network policies are too permissive, an attacker who compromises one container can probe many others. The strongest container architectures treat containers as disposable compute that should be easily replaced, while treating data stores and control planes as highly protected. That separation improves resilience because compromised containers can be rebuilt quickly, but only if the underlying systems are protected against tampering and unauthorized access. Container platforms also have control components that manage scheduling and networking, and those components are high-value targets because they can influence many workloads. Protecting those control components is therefore a core part of container security architecture. Serverless computing is another cloud capability that changes both operations and security because it removes server management from the customer and emphasizes short-lived execution. Serverless functions often run in response to events, such as an uploaded file, a message in a queue, or an API request. The security opportunity is that serverless can reduce some traditional server hardening work, but the security risk is that it shifts focus toward permissions, event triggers, and input validation. Beginners sometimes assume serverless is automatically secure because there are fewer servers to patch, but serverless functions can still be exploited through vulnerable code, misconfigured triggers, and overly broad permissions. A serverless function often needs access to storage, databases, and other services, and those permissions must be carefully scoped because an attacker who compromises the function code or its execution context can use those permissions. Serverless also introduces the risk of event injection, where an attacker triggers the function in unexpected ways to cause unintended actions or to generate high costs. Designing serverless securely, therefore, involves controlling what events can trigger the function, validating input rigorously, and ensuring the function has only the access it truly needs. It also involves monitoring invocation patterns and failures, because anomalies are often the first signal of misuse. A particular serverless risk that beginners should understand is the tendency for small functions to multiply and become hard to govern. When functions are created quickly by many teams, you can end up with inconsistent permissions, weak logging, and unclear ownership. That creates governance gaps where a forgotten function continues to exist with broad access, which is a classic long-term risk pattern. Secure serverless design includes consistent templates for permissions, standardized logging for all functions, and clear ownership metadata, so you can review and decommission functions when they are no longer needed. It also includes safe error handling, because serverless functions can leak information through detailed error messages or can create retry storms that amplify outages. In cloud environments, cost becomes part of availability, and serverless misuse can cause both technical disruption and financial harm. That is why rate limits and quotas matter for serverless triggers, especially when functions are exposed through public endpoints. The architectural lesson is that serverless reduces certain types of operational risk, but increases the importance of policy discipline and observability, because the control points are more about identity and event flow than about physical server boundaries. API security is the glue topic that ties cloud services, pipelines, containers, and serverless together, because modern cloud environments are driven by API calls. Services talk to each other through API requests, clients interact through API gateways, and automation changes infrastructure through API endpoints. If your API security is weak, the rest of your cloud controls can be bypassed because attackers can call the same interfaces your tools use. API security begins with strong authentication and authorization, ensuring that every request is tied to an identity and that the identity is allowed to perform the requested action. It also includes input validation to prevent malformed or malicious requests from triggering unintended behavior. Beginners sometimes assume that if an API is not documented, it is safe, but attackers can discover endpoints through traffic patterns and probing, and hidden interfaces often become the easiest targets because they are less monitored. Rate limiting is also essential, not only to protect availability, but also to limit abuse such as credential stuffing and resource exhaustion. Logging and monitoring at the API layer provide crucial evidence for detection and incident response, because API logs show what actions were requested and whether they succeeded. In cloud contexts, API security also includes protecting the credentials and tokens that grant API access, because stolen tokens are a common path to compromise. Tokens should be scoped, short-lived where possible, and tied to the least privilege needed for the task. Long-lived tokens with broad permissions are dangerous because they can be copied quietly and used from anywhere. It is also important to separate human access from automation access, because humans should not routinely hold credentials that can deploy infrastructure or modify security policies without strong checks. A secure design includes different identities for different functions and careful monitoring for unusual token use, such as access from unfamiliar locations or sudden spikes in high-impact actions. Another API security consideration is exposure, because many cloud services have public endpoints by default or can be made public easily through misconfiguration. Secure design minimizes exposed endpoints, uses gateways and network controls to limit reachability, and applies consistent authentication and authorization at the edge. Beginners should see that API security is both a technical discipline and an architectural one, because it is about placing enforcement points where all requests must pass. When you zoom out, CASB, CI/CD, containers, serverless, and API security are not separate islands. They form a system of controls that must reinforce each other. CASB provides cross-service visibility and policy enforcement, especially for cloud app usage and data movement. Secure CI/CD protects the factory that builds and deploys code and infrastructure, preventing supply chain compromise and ensuring that changes are tested and traceable. Container security ensures that packaged workloads are minimal, patched, properly constrained at runtime, and monitored so compromise is detectable and contained. Serverless security ensures that event-driven execution is protected by scope permissions, strong validation, and clear governance so small functions do not become unmanaged risk. API security ensures that the interfaces connecting everything are authenticated, authorized, validated, rate-limited, and logged. If any one of these areas is weak, attackers often use it as a shortcut to bypass stronger controls elsewhere. The cloud advantage is speed and flexibility, and the security challenge is to ensure that speed does not turn into uncontrolled change and invisible exposure. As we close, securely implementing cloud capabilities means treating cloud services as policy-driven systems and building guardrails that make correct behavior the default. CASB helps you see and control cloud usage patterns and apply consistent data and access policies across services, especially where shadow use and oversharing are risks. Secure CI/CD keeps your deployment pipeline trustworthy, preventing unauthorized changes and ensuring that what reaches production is deliberate and verifiable. Container security reduces risk by minimizing images, enforcing least privilege at runtime, controlling network reach, and monitoring for suspicious behavior in widely replicated workloads. Serverless security focuses on scope permissions, safe event triggers, strong input validation, and governance that keeps the function ecosystem manageable and auditable. API security ensures that the interfaces connecting everything enforce identity, authorization, validation, and rate limits while generating reliable evidence for detection and response. When these controls are integrated, cloud capabilities become a way to improve security through consistency and automation rather than a way to amplify mistakes through speed. That integration mindset is what SecurityX expects. Understand where the control points are, design them deliberately, and keep them effective as the environment evolves.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.